Hi students, we are going to be talking about division of fractions, and you've already seen some videos about it, and I know there's a lot of material here, but I really think this is a very important topic. First of all, because students struggle with it, you yourself might struggle with it, and also because I think, getting towards the end of this course, this is a real opportunity to make that connection again, that it's not just about learning the algorithms, it's not just about learning how to do a problem, it's about understanding why. So this gives us a good opportunity to kind of focus on that again for a few minutes. So in terms of division of fractions, the first thing I want to remind you about is that there is a difference between approaches and algorithms. Approaches, remember, is a way of thinking about performing an operation. What does it mean to actually do it? And we often use models to do that. Algorithms, on the other hand, are a set of steps that you can follow in order to find the quotient of a division problem or the difference of a subtraction problem or whatever it is. But algorithms are just a series of steps. Often, algorithms are taught without the approaches backing them up, and these become just a meaningless set of steps that students might be able to use but often forget about down the road. So just a reminder, for division we have three approaches, and we've talked about these approaches various times, beginning with whole numbers. And the first approach is what we call the sharing approach. You've heard the term partitive because you're partitioning. But I call it the sharing approach. Might as well keep it simple. And this is apples and buckets. There's a missing factor approach, and that's when you take a division problem and you turn it into a multiplication problem. So essentially you say, hey, what do I multiply by 2/5 to get 12/5? So that's our missing factor. And then the measurement, or the repeated subtraction, is where you're measuring out groups of a certain size. So you're saying, if I have 12 divided by 3, let's go to whole numbers for a second here, I'm saying how many groups of 3 can I form out of 12? And that's measurement or repeated subtraction. All right, so these different approaches lead to algorithms. So the sharing and the partitive, one word there, just one's a fancy word, one's the easy to understand word, and missing factor, you can use those together to explain why the old flip and multiply works. I think one of the videos said that you can't explain that. You can explain it. I've done it before. It's not pretty. I always do it in the classroom in a face-to-face setting. And it takes about 40 minutes to work with students. And we go through it slowly, kind of in that problem-solving type situation. And students see it, but then I don't expect them to repeat it. It's that complicated. So I can get college students to understand it, but trying to get elementary students to understand it, good luck. On the other hand, this common denominator algorithm, which is based on the measurement or repeated subtraction approach, that you can do, and that's what we're going to focus on. Just very, very quickly, going back to this, if I look at this division problem that I have up here, and I think about it in terms of apples and buckets, it's pretty fascinating. You start with this is your apples. I have 12/5. I mean, I'm okay with that because I could say, I have 12 pieces of apple, and each of the pieces is called a fifth. They're not whole apples, but it works. I can interpret that. This gets really interesting. This is my number of buckets. I don't even have a whole bucket. I have 2/5 of a bucket. But if you remember with sharing, the answer to a division problem is how much is contained in a whole bucket. So it gets really interesting, and that's what we do in class. It's just too much to try to do online, so you're off the hook on that. So what we're going to do is do some measurement, repeated subtraction, and some common denominator. So since I have a little bit of room left here, I'm going to take a look at this problem. Okay, so I have 12/5, and in the other videos they did it with an area model, which is beautiful. But I think I'm going to go back to using that whole idea of x's. So I've got 12/5. Two, three, four. Good thing I counted. Now I have 12/5. And remember, we just kind of have our little key over to the side. So each x stands for a fifth. And I want to know how many groups of 2/5 I can form. That's what measurement does. So 1, 2, 3, 4, 5, 6. So my answer to this division problem is 6. I can form 6 groups of 2/5. Now remember, the cool thing about this x is that I could come back here and I could change my denominators. And let's say that they're 30/3, whatever, right? So this would change, right? Each one of my x's now represents 30/3, but I still have the same number of pieces. I'm going to get the exact same answer. So it doesn't matter what these denominators are, as long as they're the same size pieces, my answer is going to come down to the number of pieces. So that's where this common denominator algorithm comes from. If I have the same size of pieces, I can do this division by just looking at the number of pieces, which is the numerator. So 12 divided by 2 is 6. All right, I'm going to clear the screen and then we'll do another example. Okay, so I'm going to do another example here. We are going to focus on that measurement approach to division and its connection to the common denominator algorithm. So I'm going to do the same thing. I'm going to say, hey, I'm going to let each one of my x's, which is just, keeping track of the pieces, I'm going to let each one be a 15th because that's what my fractions tell me they are. So I've got 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right, there they are. And then I interpret my division problem to say, all right, how many groups of 3/15ths can I make? So I set out to answer that question. And I have 1, 2, 3, 4. All right, so I have 4. I have part of a group, but I don't have the whole group, right? So we need to say, all right, how much of a group do I have? I need all 3 to make a whole group, so I don't have that. So one way I've done it before, maybe if I use a different color, let me try that. So let's say this is what I would need to make another group, but I don't have these guys in red. I only have the black one. So I have 1/3 of this last group. So that makes my answer 4 1/3. Again, I could come back here and I could change, just kind of make this easy, change my denominators to 75/75. So now each one of my x's stands for a 75th. So I changed the size of my pieces, but I did not change my number of pieces. So when it comes down to it, if I start with 13/75 and I want to see how many groups of 3/75 I can make, the answer is going to come out to be exactly the same thing. So again, I can think algorithm-wise. If I have the same size pieces, I just divide the numerators. 13 divided by 3, and you could think of it as 13 over 3 if you wanted to, is exactly 4 1/3. All right, so we're going to do one more problem. This one you can see is different in that first thing is I've got this mixed number here, but we can fix that up. And the other thing is I don't have the common denominator, so we're going to have to work on that. But the first thing I'm going to do is look at this and say, hey, I want to know how many pieces total I have here. So instead of saying I've got 2 wholes and 3 fourths, I want to know how many fourths altogether. So remember, each whole has 4 fourths, so that's 8 pieces, plus the 3 pieces here. So this is 11 fourths, right? And we're going to divide this by 2/3. So if I approach this the same way that I did before, I would make 11 x's, right? And each x would be 1/4. And then I would come back and I would ask the question, all right, how many groups of 2, how many groups of 2/3 can I get? I don't have any thirds, so I can't make any groups of 2/3. So that's where the common denominator comes in. If I'm going to rely on using the number of pieces, I have to have the same size of pieces. Well, we know how to do this. So I am going to get a common denominator. So if I multiply this one by 3 over 3 and this one by 4 over 4, I now have 33 fourths divided by, try that again, how about 33 twelfths divided by 8 twelfths? That looks terrible. 33 twelfths divided by 8 twelfths. All right, so you can see I've already drawn most of my x's. We need to get a few more in here to get 33. All right, I think I've got them now. So each x is a 12th. That happens to be our size of pieces. And I want to know how many groups of 8 twelfths I can make. So 1, 2, 3, 4, 5, 6, 7, 8. All right. There's 1. Two, so that's 1, that's 2. There's 3. There's 4. So I can get 4 groups, and I've got this 1 left over. I need 8 to make another group. So I have 1/8 of a group. I can make 4 whole groups and 1/8 of another group. Right? And there's my quotient. Again, the algorithm, all right, so here I used the approach, I used the model to get my answer. The algorithm says, hey, if you've got the same size pieces, it's as easy as just dividing the numerators. So 33 divided by 8, again, sometimes thinking of that in fraction form, 33 divided by 8 works well for people. And so if I've got 33 divided by 8, that's 4 1/8. So just kind of as a wrap up, I really love this approach and the connected algorithm for dividing fractions because I think it makes sense to students, and I am all about making sense to students.